Hi, my name is Joshua Umansky-Castro. I'm a second-year PhD student in the Space Systems Design Studio here at Cornell University, and today I'll be presenting on a project that's been my life for the past year and a half, the Alpha CubeSat. Now, for those of you who are new to light sailing, let's start there. A light sail is a thin, reflective material that gains momentum from photons. When light reflects off a surface at an incident angle alpha, it provides momentum transfer from two effects. One, from photons as they impact the surface, denoted by F sub I in the figure, and two, from the reaction of photon reflection, denoted by F sub R. The combined effect of these forces is shown here in equation 1. Sails driven by sunlight can orbit Earth and even go interplanetary, but when we incorporate laser light, we have the potential to go interstellar. Take, for example, Breakthrough Starshot. It's a privately funded initiative to send laser sails to our nearest star system, Alpha Centauri, in 20 years. It's a one-way, 4.3 light-year journey, traveling 20% of the speed of light, and carrying a spacecraft that weighs only a gram. I wish I could go into it more, but I hope that provides some of the context and inspiration for our CubeSat mission. Where's the technology at today? Solar sailing has been implemented in the past decade, with JAXA's ECROS mission kicking things off in 2010. Here we have a bit of a size comparison between ECROS, NEA Scout, which is launching on Artemis 1, LightSail 2 by the Planetary Society, and lastly Alpha, with a person for scale. Now the key thing to note is that light sail performance is not about size, but a quantity known as the sail loading number, sigma. Sigma is simply the total mass over the light sail area, and you'll want as low as a value as possible to achieve the highest acceleration. Due to the large mass of the spacecraft itself, light sails to date need significantly larger surface areas, and subsequently even more structural mass to support that surface area. Thanks to several innovations that we'll get into in a moment, Alpha doesn't need an area that large. Coming in at under 100 grams and just over half a meter wide, it can fit within a 1U CubeSat package while still achieving a loading number on par with the most efficient sails flown thus far. The innovations that make this possible are as follows. Alpha features 4 chip-scale flight computers, 2 on each side. It uses a mirror-fold technique to stow neatly into the CubeSat compartment. And instead of using booms and motors to expand the sail, Alpha's deployment is entirely passive. 2 nitinol wires woven into the sail material provide a spring force to eject and restore the light sail to its flat square shape, enabling near instantaneous deployment. While this technique would be extremely risky and impractical for larger sails, it does the job perfectly for us. And lastly, the sail material itself is retroreflective. Without going too far into the flight dynamics, what this means is that the thrust vector is always aligned with the direction of the light source. This eliminates the need for costly, complex, and most importantly heavy attitude control systems. I'm going to take an extra moment to expand on the sail's flight computers, which we call chipsets. As the name suggests, they're chip scale, a small PCB that fits in the palm of your hand that contains all the fundamental sensors, actuators, power systems, and radio comms necessary to be considered a fully functioning satellite. They were developed here at SSDS starting in 2006, and Alpha will feature the first flight of the newest generation of these chips, known as the Monarch. While the Monarch is just a bit larger than the previous generation of chips to accommodate a more powerful solar cell, it is also lighter, coming in at just 2.5 grams prior to conformal coating. There's a lot to say about the increased capabilities, such as GPS to help track the light sail, but I hope you're able to gauge some from this diagram. The big takeaway is that, with these on board, Alpha's light sail is free-flying. It's completely separated from the spacecraft that deployed it into orbit. This is a first, and a key to why Alpha's sail can perform just as well as its larger predecessors. The rest of this presentation will be about the Alpha CubeSat itself, which is essentially a delivery vehicle for the light sail, but features a number of key technology demonstrations as well. As mentioned, it's a 1U, with half of that volume dedicated to the light sail storage compartment. To hold the light sail in place, the top solar panel acts as a door. It's mounted on a spring-loaded hinge and is held shut by a latch, which in turn is held back by a nylon fishing line. The latch itself is spring-loaded, so the moment we cut the fishing line, the latch slides downward, unblocking the door and releasing the light sail. To provide a brief overview of our mission ConOps, we're deployed from the ISS with a random tumble, and there's inhibits for the first 24 hours to ensure that we don't release the light sail anywhere near the space station. Our ACS kicks in immediately to begin detumbling, specifically to spin stabilize the CubeSat around the sail deployment axis. This spin helps 1 with comms, so that the antenna is stably positioned, but 2 with the light sail, so that it is spin stabilized itself and won't randomly tumble out of the CubeSat. The CubeSat also aligns the spin axis with Earth's magnetic field, and when conditions are nominal, we are permitted to send the command that triggers the light sail release. At this point, once deployment is verified, the CubeSat has done its job. The light sail is now in orbit and can begin downlinking its own data. Now I'll briefly cover each of the subsystems, but I encourage you to read the paper for more detail. The flight code is divided into 5 modes of operation. If everything goes well, it will see only 2 of these: normal mode for nominal operations and deployment mode for light sail deployment and verification. However, if things aren't nominal, there are 3 fault modes. Low power mode cuts off non-essential power-hungry components and restores power when the battery is sufficiently recharged. Safe mode boils down the CubeSat to an even more fundamental state. It's triggered by other faults, such as sensor data being outside the expected range of values. From here, or in any mode for that matter, we can trigger specific overmode features, commands that overwrite values to perform certain tasks or to diagnose an issue. Moving on to electrical, our system is composed of 6 solar panels and a 2-board stack inside for the flight computer, sensors, and actuators. They're all commercial off-the-shelf components with a teensy 3.5 microcontroller as the computer and breakout boards from Adafruit and SparkFun for most other components. The solar panels charge 2 2000 mAh lithium polymer batteries. This voltage is regulated to 5 volts and 3.3 volts for a reliable power supply to the TNC, sensors, and the radio. On the top left of this diagram, you can see the 3 deployment verification sensors. There's a button placed under the door to verify if it's successfully opened. A photoresistor is placed below the stowed sail to confirm that the light sail actually ejected from the CubeSat. And lastly, an image is captured to confirm that the sail not only left the CubeSat, but unfolded properly. As for structure, our CubeSat is nearly entirely 3D printed and is among the first spacecraft to do so. The main exception is the rails, as this had to be aluminum in compliance with CubeSat deployer regulations. Here you can see the evolution of our chassis. All these CubeSat frames were fabricated in just a few weeks. 3D printing isn't just fast and cheap, it also allowed for very customizable compartments, such as a shelf for our batteries and of course the payload compartment for our light sail. For the flight version, we're using a printed material called Accura Bluestone. It has a bit of flight heritage and was chosen for its high rigidity, thermal resistance, and low outgassing properties. Onto the ACS. To achieve spin stabilization, we employ both passive and active techniques. First, all components of the CubeSat were distributed such that the CubeSat is properly weighted. Not only do we want the center of mass to be near the geometric center, but we want the axis of maximum inertia, the spin axis, to be as close as possible to the door axis. To transition from random tumbling to the spin stabilized state, we use a controller based on a cane damper. What's great about this model is that instead of detumbling the CubeSat and then spinning up about the desired axis, the energy dissipation effects produce a torque that will drive the spacecraft's angular momentum vector to be parallel to the desired spin axis. Lastly, we align the spin axis with Earth's magnetic field using a PD controller. As shown in the diagram on the right, the only actuation we have on board are magnetorquers that we assembled in-house. This was due to the limited space on board. But through these algorithms, we're able to achieve full nonlinear angular rate control and attitude control. Lastly, we have comms. We're the first CubeSat to fly an Iridium modem called the Rock Block, and doing so bypasses the need to acquire and maintain costly ground station equipment here at Cornell. The Rock Block transmits to the Iridium constellation and their ground stations around the world. We simply access this communications network over a web portal. We set up a control UI to send commands to Rock Block's web services, and, as seen on the next slide, we set up ground web services that use Elasticsearch to produce a mission control dashboard in Kibana. Finally, our CubeSat also features an art exhibition in space. Mounted to the solar panels and the light sail are holograms produced by artist C. Bangs with inspiration from the message plaques designed by Carl Sagan. This really ties back to the motivation for this project. ALPHA seeks to verify the behavior of holograms in space, as a holographic laser sail is actually a promising technical solution for interstellar travel. And if there is life out there, it provides a means to present ourselves, and all life on Earth, to whomever we may find, as we embark on this journey to Alpha Centauri. Thank you for listening. And with that, the authors would like to thank the Museum of Science Fiction, the Ithaca High School CubeSat Club, and generations of students at Cornell who helped bring this concept to life. Thank you to SSDS for funding this work, to NASA CSLI for providing the launch opportunity, and to Alex Burke for his technical mentorship as we bring this project to the finish line. Additional thanks to the GEM, Sloan, and Coleman Fellowships for funding my work on this project.